Hi. We're going to talk about specific gravity, density, head, and pressure. These four terms are interrelated. Understanding this will help us to better understand how pump systems function. Specific gravity is the ratio of the density of the fluid that you're interested in over that of water. So water weighs around 62 pounds per cubic foot. I'm sorry, I'm using imperial units. In the US, they're still using imperial units, unfortunately, and they're a big pump producing country, so it's one good reason to continue with these units. So if you're a metric person, you'll have to deal with it. So to give a few examples, mercury is a very heavy metal that's liquid at room temperature. It weighs around 870 pounds per cubic foot. Divide that by the density of water, we get about 14. So the specific gravity of mercury is 14. Automobile oils are lighter than water. They'll weigh around 50 pounds per cubic foot. So the specific gravity of an automobile oil will be around 0.8, maybe 0.9. So the usefulness of this term is that it tells us immediately how heavy or light we are with respect to water. So what does the specific gravity or density have to do with pressure? Well, let's say we have a tank and it's full of some liquid. Let's take water, for example, and we want to know what the pressure is at the bottom. Well, the pressure at the bottom will depend on the weight of the liquid that's in the tank. So you can imagine the weight of this liquid as tiny force vectors pushing down on the bottom. So pressure is the weight of that liquid divided by the surface area. It's a definition. It's just that simple. There's nothing complicated about that. So the weight of that liquid will depend on its density, right? So it'll be the density times the volume of liquid in the tank. The volume of liquid will depend on the surface area times the height. So if we look at the formula, we now have the pressure is going to be the density times the volume. We know that volume is the surface area times the height. We divide that by the area. We have a nice simplification where we have pressure is equal to the density times height. So typical units for that would give us densities in pounds per cubic feet. Height is in feet. We would then have pressure in pounds per square feet. So how does specific gravity now fit into this? So we know that the density of a liquid will be equal to its specific gravity times the density of water. We've just been through that. So if we put this back into the formula, we'll have pressure is equal to specific gravity of the liquid times the density of water, which we know the number for, times the height, and that's it. So I won't bore you with the details because you have to put the proper units to arrive at a consistency between the units, and it's something that you can do quite easily. But this then comes down to a very simple formula where we have pressure is equal to specific gravity of the liquid times the height divided by 2.31. And the height then has to be in feet, and you will have the pressure at with this equation in PSI, or pounds per square inch. So this is a very nice, simple, concise little formula that we can use in a lot of interesting areas. So we're going to see that now. So let's apply this equation that we've developed for pressure and head to a pump system. So say we have a tank with a pump pumping to somewhere, usually in another tank at a different height, and we want to test this pump and at least find out something about it. So the first thing we'll want to do is put a pressure gauge on the outlet of the pump. Usually a lot of domestic pumps come equipped with a pressure gauge. If not, you could put one on or whatever. So if we can measure the pressure, then we can see if this pump is operating as it should be, look at what the manufacturer says, etc. So let's say we have a pressure gauge. We measure the pressure to reach something like 50 psi. So we have our little equation for pressure that's equal to the specific gravity times the head divided by 2.31. We just turn this around to get the head, and if we're using water, we know that the specific gravity will be equal to 1. So we put the 50 psi number into the equation times 2.31, we get 115 feet of head. So that's the head at the discharge of the pump. Now, the manufacturer of a pump doesn't know what kind of system you're going to connect this pump to. He doesn't know if that suction tank is big, has a lot of water in it, or whatever. He just knows that he doesn't know anything about that. So all he can tell you is what the difference in head across the pump should be for a given flow rate. So what we need to do now is figure out how much head or pressure is there at the pump suction. So if this tank that we have is about, let's say, has a 5-foot water level, 5 foot from the top of the tank to the suction, that's 5 feet of head. There could be a little bit of friction in the suction line, but usually this is very small. I mean, if you want to assume a number, it would be much less than 1, but let's neglect that for now. So we know that the pump suction sees 5 foot of head. So the difference between those two is 115 minus 5 is 110. So 110 is the head of the pump. That is, this term is also called total head. And that's what the manufacturer will give you as a number for a given flow rate, for which you can now check your pump to see if it's operating within a certain range of what it should be doing. And that's how you use this little equation, and you can see now how useful these head numbers are, because they can be applied directly to the total head for you to compare with manufacturer's information. That's it. So, see you next time.